Yes.
Okay, it is my pleasure to welcome you to this afternoon session. And I would like to invite our first speaker, Professor Arthur Ahandje from Imperial College, who is going to talk to us about monopoles and baryon number violation from heavy ion collisions. Arthur, please share your screen, I think.
Hey, thank you. Yes, so just a minute, I will hopefully get my slides up. Okay, can you see my slides?
Yes, indeed. Thank you very much.
Okay. Yeah, so thank you very much for this invitation to speak here. It would be obviously much nicer to be there in person, but even remotely, it's great to be able to speak. And so I will be talking about magnetic monopoles and baryon number violation in the context of heavy ion collisions in particular. And basically the point, I should say, this is work that I have done in collaboration, the theoretical side in collaboration with Oliver Gould, David Ho, and Cheng Shi. And it's also, I will be saying a little bit about experiments which have been carried out by the MEDAL collaboration. And yes, so let me get started. So first of all, the key point why I'm talking about heavy ion collisions here is why they are interesting here is that they have the strongest known magnetic fields in the universe. And that gives us a completely new way of probing fundamental physics and doing particle physics. The field strengths are so high. And here you can see what kind of magnetic field strengths we can actually reach. So the strongest magnets, strongest magnets that we can build or have field strengths of around 10 Tesla, maybe 100. The LHC magnets have a field strength of 8.3 Tesla, and in GeV, in natural units, that's around 10 to minus 15 GeV squared. So that's obviously still, for particle physics standards, that's quite a low field strength. But there are stronger field strengths in the universe. There are neutron stars called magnetars, where the field strengths are around 10 to minus 5 GeV squared. And that's starting to get close to interesting values for particle physics. But where we can get even higher than that is with heavy ion collisions. And the reason for that is that in a heavy ion collision, you've got two nuclei which have an electric charge, relatively high electric charge. If you have heavy ions, it's around 100 electron charges, flying past each other at relativistic speeds. So that means that you've got very strong electric currents going in the opposite direction, very close to each other. And that means that you induce a very strong magnetic field between them at the time when they fly past each other. The strongest magnetic fields actually arise when you have an ultra-peripheral collision, which is when the nuclei just skim each other. So they don't even actually have to collide, just have to fly past each other at very short distance. There have been obviously these kind of experiments in the past, but currently the highest energies and therefore the strongest fields are with the Large Hadron Collider, where in November 2018 there was a run with 5 TeV per nucleon lead-lead collisions. And with that kind of collisions, you basically reach magnetic fields at the maximum, which are 7 GeV squared. With future heavy ion collisions, hopefully we can get to stronger fields by increasing the collision energy. But even this, as I will show, is strong enough to potentially give us access to some new physics. And the two phenomena I will be focusing on in this talk are magnetic monopoles, which is beyond the standard model. Obviously, the standard model does not include magnetic monopoles. But the other is baryon number violation, which happens even in the context of the standard model. However, that requires higher energies than we can reach with the LHC. I will start with magnetic monopoles, partly because there's more to say about them. We even have some experimental data. And just a very brief reminder. So obviously a magnetic monopole is a hypothetical particle with a magnetic charge. We know very well what a magnetic charge would look like because Maxwell's electrodynamics is compatible with those, and because Dirac showed that quantum mechanics is compatible with those if they satisfy the Dirac quantization condition, which basically tells us what the magnetic charge would need to be, and that would have to be an integer multiple of 2 pi over E, the elementary electric charge. So that tells us that actually we know pretty well what we are looking for, and also this magnetic charge is very strong. 2 pi over E, because electric charge is weak, a magnetic charge is strong, and this number is around 20 in natural units. So these are strongly charged magnetically charged particles that we are looking for. Now, one thing to say here is that obviously we know some examples of magnetic monopoles, some theoretical examples of magnetic monopoles, like grand unified theories. All grand unified theories predict the existence of magnetic monopoles. So that is a sort of concrete proof of principle that these can exist consistently in the standard model, or extensions of the standard model. However, we are not talking here specifically about any particular type of a magnetic monopole predicted by any particular theory. We are just asking generally if there are particles which carry magnetic charge. Can we find them? Can they exist? And for that, we are not assuming grand unified theory. We are not assuming that these monopoles arise as solutions of any particular theory, and therefore we also take a completely agnostic view to their mass. So obviously grand unified monopoles would generally be very heavy because they come from grand unified theory physics. But if monopoles are just elementary particles added to the standard model, there is no theoretical limit or lower limit on their mass. And so therefore the mass is a free parameter which can only be, from this perspective, the mass is a free parameter that can be only constrained empirically, and that is what we are trying to do here. Obviously, there have been lots of searches of magnetic monopoles in the past, both astrophysical searches and also in particle experiments, particle colliders. And for example, the Medal collaboration has carried out research at the LHC in proton-proton collisions. And here are the bounds that have been obtained from those. Similarly, Atlas has done a similar search. Again, the bounds are shown here. The key thing to note about these plots here is that what is shown on the vertical axis is a bound on the cross-section, the production cross-section of these particles. And so that's, of course, always what an experiment, if it doesn't find a particle, that's the only thing it can place, is an upper bound on the production cross-section. And in most cases, when you're looking for other types of particles, you can compare that with the theoretical prediction, and therefore you can actually get a mass bound. Now, the problem with magnetic monopoles is that because they have this strong magnetic charge, their production is non-perturbative. If you have a coupling which has value 20, then you can't use perturbation theory. However, that is what people often like to do with these results, because you would still like to have a mass bound rather than just a bound on the production cross section. So what people usually do is assume some perturbative process, like here the Brillian process, which are the almost vertical lines here in this plot. These here are the Brillian production cross sections, and if you compare your bounds with those, you can then obtain a mass bound, but it relies on this perturbative expansion, which is not valid because the coupling has value of 20.7. And so this means that from proton-proton collisions, we can't actually conclude that lighter monopoles don't exist. So nominally from this, if you look at these plots, you can see that nominally this would exclude monopoles with mass less than 2 or 3 TeV. But actually that relies on perturbation theory, which is just not applicable in this case. So we can't draw that conclusion. And then the question really is, so can we exclude the existence of even these light monopoles with some other way, in some other way? And that's what I'm talking about here. And there's actually a reason to believe that the production cross-section in proton-proton collisions may be a lot lower than the Brillian result indicates. And that's at least true for semi-classical solitonic monopoles, like Tufts-Polyakov monopoles in grand unified theories, which are basically the only type of monopoles for which we can really do that calculation. There's an old argument originally by Witten, later made more concrete by Drucker and Nusinov, that in any kind of process like this, when you have elementary particles colliding and producing semi-classical objects like monopoles here, the production amplitude is, or production cross-section is exponentially suppressed, in this case by 4 over the fine structure constant, which basically gives you 10 to the power minus 238 for magnetic monopoles. And so if that is the case, then of course it means that no matter what the prefactor, well, no matter what the other factors in the expression are, if you've got 10 to the power 200 as a factor in your expression, then it is going to be practically 0. And you will not expect to produce any monopoles in your proton-proton collisions. And the argument really just relies on the idea of entropy, and that is the number of different states that your collision can produce. Any kind of semi-classical state, like a Tufts-Polyakov monopole, is highly ordered, and it basically has, it's a very specific microstate, and you can count how many different possible microstates there are that could be produced in this collision, and that is basically just given by this exponential number. And therefore, this is essentially an entropy argument that it's highly unlikely that your quanta, which is 238 quanta, that they would organize themselves in precisely the right way to form a monopole. And that's where this exponential suppression comes from. So here I was just showing the picture of elephants, because that's that has been used to illustrate this point. If you collide protons at sufficiently high energies, you would have enough energy available to produce a pair of elephant and anti-elephant. Of course, it's pretty clear to all of us that just having enough energy will not produce those elephants, because there are infinitely many other types of states that you could produce. It's exactly the same with monopoles, that if just randomly you won't get those out of proton-proton collisions. Now, I should add that this argument really only applies, strictly speaking, to solitonic monopoles, and therefore we can't know whether it is universally valid. But this means that at least for some type of monopoles, the production cross-section is actually possibly very low, and therefore the mass bounds that we naively conclude from proton-proton collisions may not be universally valid. Okay, Now, so what we therefore are going to be using here is looking at a completely different way of producing monopoles, and that is using magnetic fields, as I mentioned. And this actually is a completely equivalent, it's a dual to the well-known process of Schwinger pair production, which was originally discovered by Sauter theoretically 90 years ago. And it has not been confirmed experimentally, but the theoretical basis is extremely strong. And that's just a process where you have a strong electric field and you have electron-positron pair production, essentially through quantum tunneling. That if you have a strong electric field that is unstable and that decays into electron-positron pairs, and you can describe that as a quantum tunneling process where virtual electron-positron pairs tunnel through a Coulomb barrier and therefore become real electron-positron pairs. And as I said, this has not been confirmed experimentally even for electrons and positrons, but it is believed to be true. And this can be calculated. The interesting thing about this is that it can be studied in a non-perturbative way. The rate can be calculated non-perturbatively using instanton calculus. And essentially, the rate is proportional to exponential of minus the action of the instanton. And Affleck, Alvarez, and Manton showed in 1981, so again, 40 years ago, that this can be done non-perturbatively to all orders in coupling. So the fact that the coupling is strong is actually not a problem. And for constant uniform field, the expression is shown here. So, this is what you get. You can even calculate the prefactor in front of the exponent, and so this is valid for arbitrarily strong electric charges. You're not using perturbation theory here. And now, using the electromagnetic duality, we can therefore conclude that if you have a strong uniform constant magnetic field, then in the same way, if magnetic monopoles exist, they would be produced by the dual of this process. And the rate would be exactly the same, just replacing all electric quantities by magnetic quantities. So it's given here. So what that means is that if you have a theory where there are magnetic monopoles with mass m, then you just need magnetic field, which is m squared. Just need a magnetic field, which is m squared over g cubed, and you would be producing them through the Schwinger process. Now that means that for any magnetic field that we have in the universe, we can easily calculate a lower bound on the monopole mass. LHC magnets. So when the LHC magnets were first switched on, even before the LHC carried out any collisions, you could already get a monopole mass bound just from the fact that there was not a copious production of magnetic monopoles in those magnets. And that gives you basically roughly 1.5 kilo electron volts. Magnetars, these neutron stars, take us to roughly 1 GeV, because we know that if magnetic monopoles were produced in large quantities in magnetars, that would reduce the magnetic field strength, and therefore that would not be compatible with the fact that we still observe these very strong magnetic fields. But even more interestingly, we can generate these very strong magnetic fields in heavy ion collisions. And so, as I said, with the LHC, actually we have already carried out experiments where the field strengths reach 7 GeV squared. And actually, it's only for a very short time. So the time scale, how long it remains that strong, is the inverse time scale is this omega here, and that's roughly 70 GeV. So basically, you have a collision where the nuclei fly past each other. So a very short time, you have these very strong magnetic fields. And then you can ask, how massive monopoles would the Schwinger process produce in these collisions?
5 minutes.
Okay, thanks. So we have the expression for the constant field, and that's given here, but quite obviously the field is not constant because it's very time dependent. And so instead, what we did with Oliver and David was we managed to calculate the production rate in a time dependent field of this type for at leading order. So sorry, you can calculate it ignoring self interactions, and that gives you this kind of an exponential expression, exponential of minus the mass over omega, and that's the time scale, and that's given by the red curve here in this plot. And you can see that the more time dependent, the faster the time dependence, the lower the action, and therefore the higher the production rate. We can also calculate leading order corrections to this. These are not perturbative corrections. They are just leading order in the semi-classical expansion. And we can even calculate this in principle to all orders numerically. But as you can see from the blue curve, it just becomes numerically very hard to go to high, strong time dependence. And with the LHC, we would actually be interested in this parameter psi on the x-axis to be around even 1000 ideally. So we can't reach that kind of high time dependence numerically, but we have these analytic results which give us an indication of what this production would be in time dependent fields. I should add here that we don't know what the effect of the spatial inhomogeneity, which is also, of course, present in heavy ion collisions, what that is. We also looked at what happens when the monopoles have a finite size. So the earlier calculation was for point-like monopoles. Now, Tufts-Polyakov monopoles or any other solitonic monopoles have a finite size. And you could ask whether that suppresses the production like it does in proton-proton collisions. But actually, so we managed to find the instantons, field theory instantons for these kind of solitonic monopoles. And it actually enhances, this finite size enhances the production. It's actually quite easy to see why, because it's easier for magnetic fields to pull apart two lumps of charge than it is to pull apart two point-like charges. And that actually means that there's even a classical instability. So the action goes to zero at the action is lower, so production is enhanced, and it actually goes to zero at this field strength, which means that if you reach that field strength, then you don't even, it's no longer even a quantum process, it's just a classical instability of the magnetic field. Now, this was the theory, and then with medal experiment, we've actually carried out a search for magnetic monopoles in these heavy ion collisions, and from the fact that we did not find any monopoles, you can then put bounds on the monopole mass from the LHC, and those are summarized here. And basically, this is the main plot. So there's theoretical uncertainty about which approximations we use, because we can't do the full exact calculation. So there are basically two different approximations. One is the free particle time-dependent case, and the other one is locally constant field, which is taking the fully all orders result, but assuming locally constant field. And they give slightly different bounds, and they are these two curves here. But if we take the conservative approach and take the lower of those bounds, we can say that for all magnetic charges, the fact that we don't find any of them at medal gives us a lower bound of around 100, or maybe more conservatively 75 GeV for the monopole mass. So this is actually a lower bound on the mass rather than just a cross section, because we have a way of calculating a cross section for these collisions, and therefore this is the strongest actual mass bound for magnetic monopoles that exist. Very quickly, I hope I have a few minutes more to talk about. So this was in extensions of the standard model.
Yes, you do have.
Okay, thanks. So if there are extensions that produce magnetic monopoles, then this constrains them and rules them out if they predict monopoles less than 75 GeV. However, in a very similar way, there is actually a pretty much analogous process even in the standard model, which sadly needs higher field strengths, and that is baryon number violation. So there is obviously baryon number violation in the standard model. That's well known through the chiral anomaly, and which is mediated by instantons, just like the monopole production I was talking about. What is interesting is that if you have a background external magnetic field, the action of the instanton goes down. And what we actually did, we looked at the Svaleron, which is essentially the classical configuration. But when the energy of the Svaleron goes to zero, then the action of the instanton also goes to zero. So we found these Svalerons, which describe this baryon number violation in the standard model. We found them numerically in the fields theory, and we find that when the field strength reaches essentially constant times the ratio of the Higgs mass over the W mass squared, which is here, and then the Svaleron energy goes to zero. And that means that the barrier, the energy barrier between the different baryon numbers disappears at that magnetic field. And that means that if you put a proton in such a strong magnetic field, it just dissolves classically. It's not stable, it dissolves into leptons. And so you have baryon number violation in the standard model. The standard model predicts baryon number violation if you have magnetic fields stronger than this. Putting in the numbers, it's 5 times 10 to the 4 GeV squared. And if we then look at what kind of heavy ion collisions we need, what energies we need in heavy ion collisions to reach that kind of a field strength, it is quite high. Sorry, it's 10 to the 4, 2 times 10 to the 4 tera electron volt per nucleon. So compared to the current LHC collisions, we basically need another factor of 1000 in terms of energy. Now, I know experimentally we don't know how to get that kind of energies, but what is interesting that it is only a factor of 1000. And so if you look back at how much the energies of particle colliders have increased over the decades, extrapolate that, this is actually not that far off. And so therefore, hopefully there will be some new ideas how we can reach higher energies, and then one day we can do this experiment and we can see if baryon numbers really is violated if matter dissolves in heavy ion collisions because of the strong magnetic field. I should add that these are based on the locally constant field approximation. We don't have a way of including the time dependence in this yet, and that may what we found with monopoles for time dependence actually enhances the process, but of course we can't be sure that the same is true with baryon number violation without doing that calculation. So now come to the end of this. So the key point here was wanted to emphasize that heavy ion collisions are an exciting way of probing new physics, both in the standard model and beyond, because they have such strong magnetic fields present, the strongest in the universe. Within the standard model, what we have demonstrated is that these strong magnetic fields give you baryon number violation. It's one example of what kind of effects could could have. And beyond the standard model, if you have theories with magnetic monopoles, then strong magnetic fields would produce them. And the important thing about this is that the production mechanism is independent of the microscopic details of the monopoles. It only cares about the fact that they are magnetically charged. So it doesn't matter what your fundamental theory is. These are universal bounds, and these are calculable. So therefore, we can actually place a mass bound rather than just a bound on the cross section. Thank you.
Thank you very much for this very, very nice and comprehensive talk and interesting work. Now, the talk is open to questions. First of all, do we have people in the room that they want to ask questions? Do we have? No.
Yes.
Yes.
Yes, please ask the question. Yes. Speak close to the microphone, please.
My name is Apostolos Pilavtis. So I'd like to ask a simple question. Of course, in order to get all this per creation, you need a constant magnetic field, as far as I understand. And however, within this heavy ion collision, it's not clear to me. I mean, you have done some calculation how much time plays a role, how much you should. Okay, the formula you have is just for a constant magnetic field, like that formula. But I believe you should sustain that magnetic field for some time to get this action, or the time dependence should be included, and also in your predictions. So can you comment on that, please?
Yeah, so that's a good question, and yes, so you could imagine that that's the case, but actually, for the case where we can do the calculation, which is for point-like monopoles, we find that it's actually the opposite, and the time dependence enhances the production. It reduces the action, and you can sort of understand why that is. So it's because when I think of any quantum mechanical process, if you have a very slowly varying perturbation, there is essentially adiabatic, and you don't get transitions between states. Whereas if you change your parameters in your Hamiltonian very quickly, you excite whole spectrum of states, and that's ultimately why time dependence enhances the production. You can actually see that when you have very highly time dependent field, which is the case. Here we have the asymptotic result for strongly time-dependent case, which actually is pretty much where we are heading with LHC. Then the magnetic field strength itself plays very little role. It actually doesn't. The relevant quantity is the time dependence rather than the field strength. The magnetic field is only basically needed to give you the direction of the process. That there is a process that gives monopoles. But the time dependence seems to enhance the process.
Thank you. Other questions from the room?
One more.
I have one more question.
Yes. I temporarily mute the Corfu after you ask the question.
Yes, this is for granted. You mentioned that for something even only 1,000 times the LHC, there would be enough magnetic field to see, possibly to see baryon number violation. Is it plausible that that kind of magnetic field existed in the very early universe?
We haven't really looked at that, but yes, yeah, I'm sure there are scenarios in which you can achieve that. So I think that's one interesting thing. The other is that you can probably reach that kind of energies in very rare occasions with cosmic rays, and so it may also be that these kind of events happen in even the present day universe, but of course with very low frequency, and whether there's any way to observe or constrain them. But yeah, in the early universe, yeah, absolutely, it's I'm sure it's possible to at least find scenarios in which you get this kind of strong magnetic fields. Probably not in the sort of really simplest cosmological history, but certainly in more exotic cases.
Okay, are there further questions from the room? Are there any questions from the chat? If not, I have a very quick question to ask Artu. When you talk about B minus baryon number violation, there were some works by, I forgot now, that claiming that B minus cell violation could be seen at high energy collisions because of the TeV Sphaleron height. There was also a dispute that this could be suppressed, but if you could see B minus cell violation in high energy collisions, then this approach could be quite important, I think.
Yes, exactly. And this basically comes down to this. So what we are basically showing here is that the magnetic field actually enhances this process very significantly. So if you have sufficiently high energy that you can go over the Sphaleron barrier, basically need at zero field the Sphaleron energy is 9 TeV. And it's been argued before that if you have collisions higher than that, you've got enough energy to go over the barrier. And yes, so you can have that. What we are showing here is that you don't even need to get to that kind of energy, because if you have the strong magnetic field, it reduces this barrier height significantly, and that allows you to reach with much lower energies than that.
Thank you very much for this. So let's thank the speaker again once more for this very nice talk. And let me invite now our next speaker, Professor Giancarlo D'Ambrosio from Naples University, who is going to talk to us about holographic determination of hadronic light-by-light contribution to G-2.
Okay, let's see. Good morning to everybody.
Hello? Yeah. Very good.
Do you hear me well?
Yes, indeed, and we see your transparencies.
Okay, very good. So I would like to thank, and sorry not to be with you in Corfu, and hopefully the next time will be 100% in presence in this beautiful setup. So today I will discuss the contribution of the light-by-light contribution to the G-2 is an important topic. Actually, this I will tell about the progress in this hadronic contribution. Okay, let me first do a preview of all the contribution. So we'll first discuss all this contribution and why this discrepancy somewhat is very, very interesting, or a real attack to the standard model. Then I will go to the hadronic contribution. Okay. So you know very well, everybody knows that the magnetic moment of the muon as a classical in quantum mechanic interpretation, and is very well defined the way to interact with the magnetic field. Actually, this was, we know very well, the way that one of the ways that we discover quantum mechanics and the spin, because we saw the deviation due to the magnetic field of the electrons. Simultaneously, you saw two things. One, that the spin of the electron is 1/2, but also that the coupling to the spin of the electron was not a trivial value, but was 2. Actually, this value was found not by Dirac, that not only discovered the spin of the proton, of the electron, but also this anomalous magnetic moment. We know also very well that experimentally, as many times, experiments very precise in soon after the Second World War, and they saw an experimental departure from the Dirac value of G equal to, and this put forward to compute quantum electrodynamic correction. And this was essentially the beginning of discovery of QED. Schwinger indeed in 48 computed the one loop correction, finding these values, a finite one loop correction. And then history goes where little by little you went to two loops and more loops contribution. It's interesting to point out at this point 2-3 things. First, that at that point, a generation of physicists computing Feynman diagrams was born. Indeed, a full kind of set of people started to compute higher order diagrams. And also from the technological point of view, schoolship was born to compute higher order calculations, so the modern Mathematica. So now we are computed to the fifth loop, and we arrive to a contribution of 10 to the minus 11 with a very small error, 0.2 per mil. This is for the QED contribution, okay? So this is the contribution and the actual precision in the quantum electrodynamics contribution. Then there is also electroweak correction, okay? Electroweak correction amount to be, if you compute, and actually this was a source, so what people wanted to compute at the beginning, experimentally wanted to test this prediction. So this prediction amounts to 153.6 10 to the minus 11 with this very small error. This tells you also you can compute new physics typical contribution. It goes like scale, like the mass of the lepton in the case of the mu1 square divided the new physics scale. Indeed, already in the 90s or before, wherever John Ellis for sure evaluated them, but also Maiani and Barbieri, I know, computed already contribution from supersymmetric contribution back in the 90s or 80s. And because people were expecting the new CERN experiment. And I want to stress the point that the discrepancy now, the actual discrepancy now between that I will say next, between experiment and theory is of the order of this quantity, which is kind of a punch in our face, okay? So the discrepancy between the standard model contribution and the experiment now is of the size of the electroweak contribution. So these are the two contributions I discussed so far, and the other two, the so-called vacuum polarization, which means essentially this hadronic bubble here, and this contribution is very large, and to achieve the precision in this reaching this experiment here, you have to evaluate this with accurate precision. Now we have an error of this quantity, which is comparable to the electroweak precision, and we have so-called the light by light contribution, okay, which has a larger error but is less. You don't need that accuracy actually. So here is I have here the discrepancy between the standard model and the experimental result, and you see this 4.2 sigma. And if you compute from here, you see that the size is the size of the electroweak. If you compute from this number, I put it here. Okay. Now, at this point, I have to say that my entry in this field, at least as a spectator, was at the beginning of the 90s, because people were concerned the phi factory, and they wanted to see how interesting it was to compute the E plus E minus into hadrons, so that you could have a good determination of this hadron vacuum polarization. This has been a long story. I would say this is a paper by Farley of very early, when before the CERN experiment. So at the beginning was known already. The hadron vacuum, this bubble here, can be deduced by first principle by unitarity. Why is that? Because essentially you measure E plus E minus into hadrons, okay? And this is connecting through a kernel, this is the kernel, to the hadronic vacuum polarization. So you measure directly, experimentally, the E plus E minus two hadrons. You evaluate this quantity, and this you put back in this quantity that you know, this integral, and then you get the contribution of the hadronic vacuum polarization according to the energy of the E plus E minus two hadrons. Okay, the important point was known already from a long time, that a major contribution come from the region of the E plus E minus individual hadrons around the rho region. You can see even here, 500 is the contribution of the rho, and very small the rest, onto the effect to the G minus 2. So from the beginning, the question is, okay, we have to measure E plus into minus two hadrons very well, and by unitarity, we give the contribution to the G minus, to this contribution of the G minus 2 of the muon. Now, back then, there was the contribution of the light by light. And this, here we came all the harm, because this is the original paper by, in that period, in the 90s, by Kinoshita. And he had several ways to do the calculation: free quark model, pion, raw intermediate exchange, and he had a very hard time to find a unique value. Okay. Let me tell you one thing that is important. Let's say that already in the 70s, one knew how to do calculation with hadronic physics, because Weinberg told us something. If you have a here we are talking about hadronic vacuum polarization, you are talking about a two-point correlator. And the two-point correlator typically can be left, right, and he knew right away that he has two sectors, if you want, the quarks point of view, where here there are quarks at high energy, and the low energy, where there are pion and vectors. He wrote this then as a spectral function, as rho, pion, and axial, according to you have vector and axial. And then he found, according to this sum rule, he found a two-sum rule, because he required that these to go to zero, as was required, had to go smoothly, so faster than q squared and q to the fourth. And this made a success of the so-called Weinberg sum rule, and here you get so-called the vector mesodominant, the value. I want to show here the Aleph data, how good they agree with this prediction. So you see, only a few GeV, you may incite contribution that are beyond this one particle exchange, and beyond the rho and pion dominance. And this goes to what is so-called the minimal hadronic ansatz. The minimal hadronic ansatz is very simple. Is to divide very naively the region in essentially two regions. one very low energy, where the regime of chiral perturbation theory, dominance of the pion and the rho here. And then a high energy, you use perturbative QCD. You use an interpolator among these two regimes, and you find your 2-point, 3-point, 4-point correlator. This was a traditional attitude, okay? Indeed, already in 93, people, the Raphael said, no, we can compute everything for the G-2 because we have a very powerful tool matching between low energy physics, then high energy, and you do correlators, okay? Let me tell you the important result and tell you a little bit more about the G-2. So you have two regimes, QCD, and then the regime of chiral perturbation theory. And typically you have a 2-point correlator. And the 2-point correlator you can write in terms of quarks, high energy, and a more, you have a QCD correction, but you replace that with pions and vector. Let me tell you that higher order coupling here and the KPT were very well described by Vector Mason-Dona, and even you can do a matching here. So you can even put a full tower of resonance, you can do even better. I want to stress one point that is at this point, that for the 4-point function of the G-2 is important also the pi-0 exchange. You may exchange essentially West Zumino-Witten terms square. And so this is important. So not only the so-called even parity term, but also odd parity term in the Lagrangian you have to write. But what the Raphael proved, which is very nice, in 2002, 2001, 2000, when essentially the first Brookhaven data came about, he said, okay, I have the 4-point function here, okay, fine. I have a cutoff of my theory at 1 GeV, typically. Then I have here, I have my Lagrangian here, which include also the West Zumino-Witten terms. I know all the couplings, West Zumino-Witten, pion, F-pi, and things like that. And I put a cutoff M. Then I obtain the leading log approximation of the contribution to the light by light, because depend only the mass here, the mass of the muon, and the mass of the cutoff 1 GeV. So this is known perfectly in terms of the West Zumino-Witten terms. Then there are some leading log, but the leading large contribution is known from this, from the pi-0 exchange. This was the discovery, if you want, in 2001. And so now, it's important, as I've tried to emphasize, that you have a matching between your hadronic contribution from the pion and the QCD. Okay, what another important discovery, according to me, was some interesting point regarding the 4-point function, which was discovered by Melnikov and Weinstein. Melnikov and Weinstein said, okay, I have this is the pi-0 exchange, this is the external magnetic field here, you have a 4-photon here. If I send the Q square a large momenta, I have a new constraint from short distance coming from the fact, if you want, that this can reduce to a double triangular diagrams. And this gives a new, well-known constraint from short distance. Indeed, this is the so-called Melnikov and Weinstein limit. Q1 and Q2 are the ones that are in the loop. Q3 is the other one that is in the loop, but is connected to the external magnetic field. So he said, here in this limit, I have a new limit that whatever theory are, they have to satisfy. And this is important because we want to evaluate well this contribution. So they did a model, actually. They did a model in which they put a pi-0 and an axial. And compared to the evaluation of the Raphael, Knecht, Niffler, they found a substantial enhancement by this new constraint. But there was something funny.
5 minutes. You have 5 minutes.
Okay, very good. There was something funny about this. The funny thing is that not all the low energy theorem was recovered by Melnikov and Einstein. So if you want, their model had a beautiful short distance behavior, but somewhat was lacking of a good low energy phenomenology. In the meanwhile, a new approach, beautiful, essentially follow up of the 2-point function of the theorem I told you of unitarity, but this was evolved by Gilberto Colangelo et al., in which they try to do a theory with dispersion relation, which with the arrive to 4-point function. We instead use the so-called holographic. The main reason I like holography because as a non-traditional approach. So holography knows very well this behavior. It promotes the QCD behavior to conformal, then is obliged to have a tower resonance, the Kaluza-Klein states, and then it arrives to low energy, and you get what you get. There are a set of models, several. I like one, I think is perfect, is the one by Hirn and Sons, very similar but better, the one of more famous Sagai Sugimoto. I like less the one of Pomarol, Darold, because they have a scalar field in the bulk, and this is, according to me, disputable. So you have only gauge field, and the pion means chiral symmetry breaking is obtained by breaking, by having boundary condition, by breaking by boundary condition, essentially. And the pion comes naturally, except is massless, but is a natural result of this breaking of the 5-dimensional boundary condition. And you have a nice theory which predicts Gasser-Leucht-Wheeler coefficient nicely, 2-point function, as we say here, the 3-point function, and as also address the issue of the 4-point function. The main point I will stress the result is that compared to the work by Melnikov and Einstein, has no local contribution generated by the full tower of axial. And this is a new novel contribution. And this is is different from the Melnikov and Einstein. And recently, this is the result essentially by Gilberto Colangelo, which used a different model, but substantially confirmed. So these are the contribution essentially to the G-2. Here is the plot for the Melnikov-Einstein model. And here our contribution and the contribution by Gilberto Colangelo. We agree with him and with our, essentially with the white pager. This is after our paper, and use this tower of states that you have axial. Let me tell you that I suspected this in advance because the argument since Weinberg, Gasser-Leucht-Wheeler, vector meson dominance tell you that vector and axial, they must play a very important role. Numeric.
Time is up. Sorry, we are really pressed by time. Can you summarize, please?
Yeah.
Thank you.
As you know very well, the problem is not in the light by light, but in the vacuum polarization. And this is a disaster because it's a 2-point function, and the lattice appearance disagree with the dispersive approach, and we don't understand this. This is an intrinsic problem of this. I will summarize that the lattice result have to be understood. I find the discrepancy huge order of the electroweak correction, Light by light, on the contrary, I didn't say that, but even lattice agrees with our result. And the only thing I fear, but I hope, is in general, these light by light, not light by light, G-2 every 20 years, you have a new experiment. And so you have breakthrough every 20 years. Let's hope we don't have to wait, but I don't think we'll wait 20 years to solve this issue. Okay, thank you. Thank you.
Thank you very much for this very nice talk. Let's hope that in 20 years in Corfu, you will we will see some new results. We have time for a couple of short questions. Fresh from the room.
Yeah, there is one question.
Yes, please.
Hi, Giancarlo. This is Paul Franklin. And
hi.
We had a discussion at this conference last week about BMW, which I think is Budapest, Marseille, Wuppertal. And
Yes.
the conclusion, well, Matthias Neubert seemed to have looked at it, and the question was mainly the question of the uncertainties in that calculation. Because if that calculation is correct, then the discrepancy goes almost completely away.
Yeah. I like a lot this point. Indeed, yeah, I agree completely with Matthias, because you see, I try to emphasize maybe the error on the. Okay, let me go here. That is, you see. Here, this calculation from the theoretical point of view, at least from the analytic point of view, let's say, is very well known. And we fit the data, the dispersive, let's say, the dispersive approach, okay? However, the requirement that lattice must have a small error, as I said before, is very strong. So you really have to have everything under control. I agree completely with this point. So I'm not an expert to judge lattice, but I think the requirement for lattice people to have such a small error is very strong. Did I understand correctly what you want to say?
You need to unmute the Corfu, because I always mute you when to avoid yeah, good. Please go ahead now.
It seems that before inventing new physics, one obviously needs to know the status of these hadron contributions.
Yeah, well, so, but I don't understand. Matthias Neubert attacked the dispersive approach or the lattice result? Because the discrepancy is internal. You see, the main thing is that here appears that there is an internal discrepancy between theorists, let's say, only theorists, between lattice and dispersive. This is the major discrepancy.
Probably. No, Matthias is, I don't think he's an expert on lattice QCD. But,
yeah.
I don't think he mentioned the dispersive approach, actually.
Yeah. But so then...
lattice needs to be the most accurate in principle than the dispersive approach.
Yeah, but because if the dispersive approach is correct, then we have new physics. This is the point. If lattice approach is correct, then we have, if lattice approach is correct, we have a standard model. So the question is, hadronic vacuum polarization. The hadronic vacuum polarization is this value or this value? If it's this value, which means lattice, then we have no new physics. If instead the result of the dispersive approach is correct, then you have a discrepancy between standard model and this.
Okay.
Okay, I'm afraid since we are running late of time, I have to cut short this interesting discussion here. So let's thank the speaker once more for this very nice talk. And let me now pass the chair to Professor Jan Kalinowski, who is going to invite George Savidi from Democritus Research Center, who is going to present an online talk on gauge field theory, vacuum, and cosmological inflation without scalar fields. Jan, the chair is yours. Thank you. And please make co-host Jan Kalinowski as a chair.
So thank you, Nick. Actually, you introduced already the speaker. So maybe I can just simply ask George to share his screen, and then you have 25 minutes for the talk plus 5 minutes discussion, and after 20 minutes I will give you 5-minute warning. Okay, thank you.
I think that I already make a sharing screen. Now I will make enter full screen. Okay, did you see the whole screen?
Yes.
Okay. So I will talk about influence of the gauge field theory vacuum on the Friedman cosmology. So this is some titles which I will go through. So there is a discussion in the literature, and that the vacuum, the 0-point energy contribution to the cosmological constant is usually is almost infinite. And but recently Donahue he calculated not just energy density, but also the pressure. And you can see here that energy momentum tensor has this form, and if we take the trace, it's equal to 0, and therefore the vacuum contribution, 0-point contribution to the energy momentum tensor and to the cosmological constant actually is equal to 0. So the calculation of effective Lagrangian by Heisenberg and Euler actually is an example of the to calculate the contribution of vacuum fluctuations and obtain finite gauge and renormalization gauge invariant results. So only the difference between vacuum energy in the presence and in the absence of external sources has well-defined physical meaning. That's the way how one should get finite results. So this is I show the Heisenberg-Euler effective Lagrangian, which is the sum of all one-loop diagrams in QED. So it's well known, therefore I will not spend some time to comment on this expression. This is a behavior at weak fields and at strong fields, and there is the zero charge problem, which everybody also knows. So 2 years ago, I was considering the massless limit of this Heisenberg-Euler Lagrangian, and I got this expression, which you see here. It's just a classical part plus quantum corrections, and it has very beautiful and simple logarithmic term, where F is the h square minus e square, magnetic field minus electric field square, and product is equal to 0. So having the effective Lagrangian, one can use formula derived by Schwinger in his famous article to calculate the quantum tensor energy momentum tensor. And if we substitute this expression into the T mu nu, one can get expression for the energy momentum tensor, which is written here. As you see, it is a classical Maxwell tensor, T mu nu with M Maxwell. And there is this quantum correction. And there is a term which is proportional to the G mu nu times field. So long ago in 77, 76, 77, there's a lot of publications to find the effective Lagrangian in Young-Mills theory. There is expression which I show here, where F1 and F1 are just eigenvalues of the field strength tensor. So this expression amazingly can also be integrated. The proper time integral can be taken exactly, and one can see here on the first line is the effective Lagrangian coming from the gauge field theory for SUN. This N is SUN, and you see that there is a different signs. For example, in Young-Mills theory, the quantum correction contained here the minus, and QED part is with plus, and F is a number of flowers, number of flowers. So this expression, if one calculate, one can again calculate energy momentum tensor quantum, and you can see it here. So it is a classical expression for the energy momentum tensor, T mu nu Young-Mills, plus this quantum correction, and there is a term which is proportional to the G mu nu. Now, if you calculate the T00 component, which is energy momentum density, one can see that there is the curve is going the way as you see on the figure, and there is a condensate which is proportional to the lambda Young-Mills dimensional transmutation. Here is it happening, and the condensate is proportional to the lambda QCD. No, I just take for SUN. Okay, as far as we knew the energy momentum tensor, it became clear to me many years after this result that one can calculate the energy density, which is written here, and the pressure. So having this energy density of the vacuum and the pressure, we can actually we have the quantum equation of states of the Young-Mills vacuum. So if one substitute the value of the condensate, then one can get this expression which contain only dimensional transmutation parameter, this lambda Young-Mills. So this is a quantum equation of states which I will use in my further calculations. So if one draw the function of energy density as a function of pressure, you can see this type of graph. One can calculate, one can see from the previous formulas that pressure is equal epsilon divided by 3, which is relativistic gas, or let's say of photons. But there is additional term which says that the pressure actually is larger than for relativistic gas. And one can calculate also the parameter W, which is pressure divided by epsilon if the equation of states parameterized by P equal to epsilon, W epsilon. So you can see that there is a regions where energy density and pressure are negative. There is places where the energy density is negative but pressure is positive, and there is places where the energy density and pressure both are positive. So this is a equation of states for Young-Mills. Now, as far as we have energy momentum tensor, we can see how the influence of this quantum energy momentum tensor on the evolution of Friedman cosmology. So first of all, one can see that there is a contribution to the cosmological constant, which is written here, and it's expressible in terms of lambda Young-Mills, or lambda QCD, if it is SU3. But I want to stress that it's not stationary. So I will explain what I mean. So there is two equations of Friedman. First one contained the first derivative of scale factor, and the second is acceleration. So as far as we knew the epsilon and p, we can calculate the sum epsilon plus p, which has this expression, and epsilon plus 3p, and obviously one can see that strong energy dominance is violated by these expressions. So I did not put all the details, but what happens is that the scale factor, if we write the scale factor in the form written here, but there is a A0 time A tilde. A0 is so A tilde is dimensionless scale factor, and we introduce the time tau, which is through this scale L, which is expressed through the gravitational coupling constant and lambda Young-Mills. So equations for A tilde, for scale factor, has this form. So K can be flat or sphere or hyperbolic, and parameter gamma square is a ratio of the scale L, fundamental scale, I will say, to the initial parameter, which is A0. So if you look to this equation, first of all, scale factor should be positive, and this means that this root also should be to have real values for scale factor. This expression under the square root should be positive, as in Friedman cosmology. Actually, it is almost the same. So if you see the behavior of this under the root expression, it depends only on this parameter gamma square. So for small gamma square, the curve has this form, and this means that allowed value of scale factor either are in this small region from 0 to that maximum value, or from this value and up to infinity. When the gamma is increasing, the curve is going up, and there is only one point where the solution exists solution, and then the place where gamma square is large, then all values of A are available. This defined the type of solution, which I defined type 1, type 2, type 3, and type 4. So if we substitute, if we calculate the second acceleration equation, we see that epsilon plus 3p has this form, and you can see that this expression is positive here. Therefore, strong energy dominance condition is fulfilled, but this area where B is positive, one can see that epsilon plus 3p become negative, and therefore there is a positive acceleration. So what I want to say that during the evolution, at some moment of evolution, there is a deacceleration in this area, but in this place there is acceleration. There is acceleration, non-zero acceleration for finite, not finite, but I will say that some essential acceleration, which finally drops to 0. So this means that acceleration have a finite duration, I will say. Now, as far as solution, if we solve because one can solve the equation, one can express the vacuum field strength tensor as a function of scale factor, energy density, pressure, the expression between pressure and energy density. One can calculate the behavior of the W. One can calculate the dependence of Hubble parameter as a function of scale factor. One can calculate the acceleration parameter and also omega density, vacuum energy density. So I have no time, I think, to discuss all the solution, but I will concentrate on one of them, the type 2 solution, which has initial acceleration of finite duration. At that case, the gamma square is bigger than 0, but less than 2 square root of E. And I don't see this. A is larger than mu2. So if we parameterize, if we make the substitution into the equation, which is this mu2 to the power of 4 E times B squared. So for B, we got this equation. And actually, the solution is expressed in the so-called Lambert-Euler function, which is written here. So this parameter mu square is larger than square root of E and less than infinity. And gamma square mu2 square is bigger than 2. What it means, it means that the expansion of the universe, in this case, is started not from 0, but from the minimal value mu2, which I already show somehow here, you see. So here, the scale factor can be only positive, and it is from non-zero value. So one can calculate the acceleration parameter. One can see that it's always negative, so there is acceleration. But this acceleration is very large at initial time of expansion, and it is drops to 0 as universe expand. So one can calculate also W parameter, and it is initially is -1, but then when B started increasing, then it goes to just to relativistic gas. Also, the Hubble parameter can be calculated, which is written here, and omega. So now you can see the graph. I just put it here. So as you see, the initial, this is a scale factor. So you see that it started not from 0, but from non-zero value, and it is accelerating and then become to the standard behavior. So you see that field strength tensor is at the initial stages is large, but then drops to 0. The energy density is negative, but then also drops to 0, and the pressure also, as you see, is large at the initial, but then also drops. So therefore, it goes to almost flat expansion. There is other quantities also. For example, here you see the behavior of the Hubble parameter. You see that it is it has this bump, but then it again goes to 0, and this is of course mirror of the fact that, as you see, the acceleration parameter is negative and then goes to 0. Therefore, it becomes somehow influence of the gauge theory vacuum is after it accelerates, it drops, become 0, and the same with omega 2. So there is also the type 4 solution. It corresponds to the this curve when the gamma, because it is large, there is no solution, and all values of A are available from 0 to infinity. That's a type 4 solution. And as you see, it started the scale factor. There is a deacceleration, then there is a stationary behavior, but then in the late time acceleration, which comes here, and this is the acceleration parameter. One can clearly see that for at the initial stages of the expansion, the acceleration is there's no deceleration, right? Is actually negative, but then in this place at the late time it becomes positive. So therefore, I will say that here is the this solution shows 4 stages. One is the acceleration here, then we have scale factor is the acceleration is negative. Then there is a stationary behavior, and then there is a late time acceleration of finite duration. So I just show you the Hans Euler and Werner Heisenberg, which they did this beautiful work. This is a Sommerfeld, where they discuss the creation by the magnetic field, electric field. I'm sorry, that was actually one talk before a discussion of the pair.
5 minutes left.
And this is the Werner Heisenberg visiting Democritus in 50s when there was a accelerator was built. So thank you very much for your attention.
Are there questions in the room? Oh, Apostolos Pilaxis has a question.
Very interesting talk. I do not understand the whole setup. So in the beginning, you have some condensate of, let's say, of glucose, whatever, I don't know, which is displaced and transfers time from the vacuum. I do not understand. I mean, in your case, this calligraphic F is just somehow the energy, but how the...
Calligraphic F is a field strength tensor.
Yeah, okay. But how the time dependence of this F, I understand that plays a role, a kind of inflaton. So how the time dependence enters for that expression?
Oh, yes.
I know for the constant, I mean, you have cosmological constant, you have a...
Yes.
But you need the field as well, you need something like...
The reason is that in gravity, there is no covariantly constant fields. So if you substitute epsilon, so we have here the epsilon of F and P of F, right? So if you substitute it into the, so you see this expression when you...
Yes, F could be constant, still could be constant. There's no problem with that expression.
No. This F depends on time. This F depends on time. So when
you need an equation of motion for that as well.
Yes. So the whole story is the fact that this F, the field strength tensor, is changing with time. I did not show this. I cannot show the equations. That's what's happened. So therefore, what I want to say that the gauge field theory vacuum is not in this place. So what you have seen during the talk is the field strength tensor is moving around this curve, and that's why at some moment there is no acceleration. When the field is here, there is acceleration, but when it goes in this place, the acceleration stops. So that's why it is of finite duration.
Okay, so you need to assume some initial conditions for it, as far as I understand, right?
I don't know what you mean by initial conditions, but what I was saying that this
You need to assume that it's placed from the minimum. That's what I'm saying.
Yeah. Gauge field is not in the minimum all the time. That's the story. Because what happening is that gravity force the field to move, not being in the. That was initially myself. I was thinking that because it's on the condensate and it is large, then there will be huge contribution, and that does not work. But what happens that actually gravity force the fields move around, and then at some moment it is large, that give acceleration, but then it goes away from the minimum, goes to some places where the field is small. There's no condensate. That's why the behavior of the solution is as you see here.
Are there any other questions in the room? I don't see. And on the web, do we have any? I don't think so. So I think that we should thank the speaker again, and also all the speakers of the morning session. And we will meet after lunch at 4 p.m. Thank you.
Thank you.